All right, so we're going to call this 7.5 pH and stoichiometry. So we're going to actually combine our knowledge of pH and our knowledge of stoichiometry into one kind of large type of problem. And we're going to look at only one example problem for this lecture because you really actually have all the tools to do this. You just need to know how to put them together. So I'm going to put that problem up here, zoom in a little bit on us. And so we've got a student that's going to add 40 grams of a base, sodium hydroxide, to a 500 milliliter sample of 3.4 molar hydrochloric acid, HCl. What we want to know is what's the pH of the resultant mixture. Now, if I were to ask this question and I didn't have any base in there, if I asked you like what's the pH of a sample of 3.4 molar HCl, well, it would be really simple. We would just use the pH equation that we learned at the beginning of this unit. The concentration of the H plus is 3.4 molar. You plug the 3.4 in for H plus and you solve for pH. But this particular problem has a twist in the fact that we are actually adding a base to that particular solution. And so what's going to happen is our pH is going to change. It's going to alter a little bit. So what we now have to ask ourselves is how much of this H plus is going to remain when the reaction is complete, after the reaction is over. If you go ahead and write out the chemical equation, which is always a good start for a stoichiometry problem, you're going to get this. You'll notice that there are no coefficients in front of any reactants or products. I did that on purpose to make this first problem fairly simple. And because there are no coefficients, we should know that 1 mole of sodium hydroxide will consume 1 mole of HCl, which is an important point for us. All right, so let's attack this problem. Again, we would love to get to the point where we know how much hydrogen, how much H plus remains after the reaction. And so to do that, let's go ahead and compare the moles of acid that we have with the moles of the base. That's a good starting point. So I have two pieces of information here about my acid. I know the volume and I know the molarity, so I'm actually going to start with my acid. And I want to figure out how many moles of the acid are actually present. I've got 0.500 liters. And I know that the molarity of that solution is 3.4 moles per liter. If I do the math on that real quick, that's going to come out to a total of 1.7 moles of HCl. Now let's go ahead and take a look at the base. How many moles of the base are actually present? So for my base, I'm actually not given a volume. I'm going to go ahead and erase this. For the base, I'm not given a volume. I'm just given a mass. Interesting. So, well, let's start with that number, 40.0 grams of the sodium hydroxide. And again, my goal is to get that into moles. Well, yeah, this is where your periodic table comes into play. The molar mass of sodium hydroxide is about 40 grams per mole. So if we rotate that, that's 1 mole per 40 grams. G's cancel out. And in this mixture, I have 1 mole of the base, or sodium hydroxide. Now, if you'll recall, up here, I said that for every 1 mole of sodium hydroxide, it will consume 1 mole of HCl. You might ask, well, how do we know that? Well, that's again from the coefficients, the 1-to-1 coefficients in the chemical equation, right here, 1 to 1. So what that tells me is that this 1 mole of sodium hydroxide means that that will consume 1 mole of HCl. And again, we can only make this 1-to-1 comparison if the coefficients are 1-to-1. If the coefficient is 1-to-2, then we have to do a mole-to-mole ratio. So, what can we do with that? Well, that's telling me that we will consume 1 mole of HCl when we put in the base. So let's go ahead and subtract out 1.0 moles of HCl. If we do that, we're going to come up with 0.7 moles of HCl that remain. And look, that's what we were looking for, what remains after the reaction. Now we can insert that value into the original equation that we felt we needed to use to solve this problem. So the pH is going to equal the negative log of 0.7. And I did that on my calculator, and that's going to come out to 0.154. So that's how we combine a pH and stoichiometry problem.